What's up, guys? Welcome back to another physics video. Oh my God, we're in electricity and magnetism now. Isn't that crazy? Um, so on the date that I'm recording this, it is the 18th of February, um, and it happens to be National Pluto Day. So shout out to Pluto. Um, I'm gonna dedicate this video to some special people in my recitation section for this class. I won't say their names because I didn't ask them if I could. But if you're watching this video, you know who you are. Um, but yeah, okay. So this is the this is the exam one review, or this is exam one from 2017. Um, we're gonna jump right into this. Some things to have some things of note, I think, on this formula sheet here is we've got Coulomb's law, which is nice to have. We got the volume of sphere and the volume of the area of a sphere as well. And then we have some pretty useful integrals that I believe we use at a certain point. But let's just get right into it. Um, okay, so question one, we got four charges are fixed at the positions shown. The distances A and B are known. Okay, and this is A as well. Um, the charge at Q equals negative A is negative. So this is at negative A, 0. I'm just going to get rid of this. And then the charge on the y-axis are positive. So this is 0b. This is 0 negative b. And then the charge Q3, find the force that would be exerted on Q3. Okay. The charge so it's positive. So this is A0. Okay, so find the force that would be exerted on the charge Q3. Okay, so we'll be using Coulomb's law for this question, as you know. This is on the formula sheet. So there we go. Okay, so the first thing I would do with this question is I would draw vectors from these points here. So since Q3 is our reference point, we want to be drawing vectors towards it or away from it, right? So Q2 and Q2 are both going to have vectors pointing straight at Q3, right? Um, and that's important. So the components of this vector will be pointing as such, or as so. Oh, wow, this is horrible. Okay, this isn't going very well. There you go. Okay, so let's tackle those guys first. So we have that. Oh, I'm actually going to flip the. Sorry. Actually, no, that would be bad for a YouTube video. Let's not do that. Sorry. Okay, so force from charge Q2 onto Q3. And then we'll do, this is the first one. So we'll just say this is the top charge. Top charge. So the one that's at 0b. That's going to be equal to, I'm just going to write K because I don't want to write the constant over and over again. And that's going to be Q2, Q3, because they're both positive, over R squared. So what is R in this situation? R is going to be for Q2 and Q3, we have the square root of A squared plus B squared. And that's because this is a distance B away from the origin, and this is a distance A away from Q3. So that's what R is. R hat would be A over that magnitude, IX plus B over A squared plus B squared, IY. And yes, it is 1:30 a.m. We got that grind. We're on that grind, but all right. So we've got the things that we need the most. So we're going to plug R into that, and so that would just be A squared plus B squared. I believe. And then we have, well, we can go ahead and just make this 3/2, I believe. Yes. Um, and all I'm really doing is multiplying this denominator into the denominator here. So from r hat into this. So it's just making the 3/2. And then we'll have our vectors, which is just aix plus b I y. Okay, so that's our first vector. And then we'll say the bottom q2, so the one that's on the negative b, at negative b, or 0, negative b, or we have f2, 3 again. That's probably a bad, format, but that's okay. q2, q3 again. And then same thing. It's a distance. It's the same distance away from it. It's the same r squared, but the components are going to be different. So we still have aix because it's still in the positive x direction, but it's in the top charge would have a negative biy, and that's because it's pointing down, um, down the negative x-axis or negative y-axis. I apologize. Uh, the bottom charge is pointing up, so up the positive y-axis, and so that would be biy. Those will cancel out in a second, but we'll get to that. And then we have charge negative q1, so this would be 1 onto 4 or 1 onto 3, charge 1 onto 3. And that's going to be q or k times negative q1 times q3. And this is going to be over, I want to say 4a squared because it is a distance 2a away from q3. So it's going to be 4a squared because remember we're squaring the radius. And then it's just going to have a vector in the x direction because there's only one component that we care about here, and that's it's pointing in the positive x direction towards. Sorry, I lied. It is only in the x direction, but it is pointing towards q1. That's why it's negative. So I don't know if you guys can see that, but that is what we're doing here. All right. Okay. Cool. Should make this black, and I'll make this red. Okay. There we go. Cool. So that's the negative is going to take care of itself. But now what we need to do is find the force on charge Q3. So what I would do is then separate the components into the X and Y components. We're just adding these up, right? So in the X direction, we have, okay, so if we add all these forces up in the X direction, the X component of these forces, and what I'm saying by that is like only adding like this to this to this, okay? Neglecting the I component, the Y component, I mean. And so that's what we're going to do. So they're practically the same thing. So they are the exact same thing. So you'd have 2 times K, Q to Q3 over A squared plus B squared to the 3/2 power. And then you'd have this A up top from that component. And then that would be it. Plus, or minus really, K times Q1, Q3. And the reason it's minus is because Q1 is negative, over 4A squared. Okay. And that's supposed to be equal to 0 because remember we want the force on, find the force that would be exerted on charge 3. Well, we've technically already done that by expressing all these. So next we want to add y. And the next part of the question is find the value of q1 that would make the force 0. So we'd have equal to 0. Okay, we'll solve for that in a second. And then we have y in the y direction. But if you can tell already, this was just b0. There is no y direction of the force. And the reason that is because of symmetry between q2 and q2. Because they both have vectors, components pointing in the same direction exactly at each other, they're going to cancel. And q1 doesn't have a y component that is acting on Q3. So there we don't really care about y, which is good. So we just need to use this equation to solve for Q1, right? And so what we're going to do is do 2k Q2 Q3 a over a squared plus b squared 3 halves. That's going to be equal to k because I just added it over Q1 Q3 over 4a squared. Okay, we cancel out the k's. And we're solving for Q3, but we can also cancel out, I mean, we're solving for Q1, so we cancel out Q3s. And then we can multiply the 4a squared over, so we would get 8a cubed, 8a cubed, Q2. That's just because a squared times a is cubed. And then that would be over a squared plus b squared, 3 halves. And that equals Q1. All right, so that's our final result here, is 8a cubed, Q2 over a squared plus b squared to the 3 halves power. Okay, that's our final answer. Final answer. That's our final answer. Um, and that is right. I'm looking at the answer key. So I'm kind of cheating, but that is our final answer. Okay, cool. So we can move on to the next question. Okay, so question 2. There is a charge Q1 uniformly distributed along the x-axis from the origin to x equals L. Find the electric field at the point x equals 0, y equals h. Okay, so here is x equals 0, y equals h. Cool. Okay, so the first thing I would do on this is immediately draw a vector from the line charge. And I would just draw it, anywhere you want. It's just going to be an arbitrary piece of this. So I will draw it from here if it makes an arrow. Okay, it's not making an arrow. I'll just make it myself. Okay, cool. So we've got the arrow pointing from the line charge. And a general rule of thumb is if we're not really told exactly what the charge is or the sign of the charge, we can assume that it's positive. All right, so that's why it's pointing away from the line charge towards the point at 0h, for those wondering. And then we want to draw the components as well. So we have the x component and the y component. And so basically we have this vector here, and we'll just call this r. And it's got its components, the x and y component. Okay. So imagine there's like an angle theta here. Right? This would be x and this would be y. X and y are sine, cosine. So what we need to do is, well, the law we would use for this question is electric field law, or the field, this thing, lambda 1 over r squared, r hat, dl, I think. Yeah, so it would be dl. Okay, so step 1 is we want to do this by parts in a component form. And so what we want to do here is first do ex. Well, actually, let's identify something. So first we have lambda. What's lambda going to be equal? Lambda is the charge over the length of the object that we're looking at, which in this case is L. R is going to be equal to, and this R here is going to be equal to the square root of, wow, that's bad, h squared, or really, so this is a little complicated, but not really. It should be L minus X, if I'm remembering correctly. I did do this earlier. Just want to make sure I did a good job of it. But this should be L minus X squared plus HX squared. Yes. And the reason that is because this vector that I have drawn here is going to be changing with respect to X, right? So imagine we have, here's a line vector, here's another line vector from a different position, a different position, and we are moving along this object, right? and it's with respect to the point x at which it's originating from. So the y component or the x component of this vector is going to be a function of x. Wow, it really doesn't want to draw a line for me today. That's mildly irritating, and I can't draw one either. But okay, so that's why that is, and then the y component stays the same, but the x component will change. Um, and so say like we want to take a vector from this point or from this point, then that would be some arbitrary value of x, and we're subtracting that from L. And so that's where we know it is from, right? And then when we're at L, actually, then yeah, mm, yes, yeah, okay, that was right, yeah. Because then, if we're here and we have this arbitrary value of x, then this is L minus x, and that's the length of the x component of the vector. Okay, so cool. Let's move on. So that's what R is. R hat is going to be equal to L minus x over R Ix plus, oh, this will be negative, by the way. It's in the negative x direction. It's pointing away from x equals well, L. So then we would have H over the same thing. I hat Y. Okay, cool. So let's do EX first. So electric field in the x direction. So, and also I forgot K. So K goes here. So we have K, Coulomb's constant, times the integral from 0 to capital L, because that's the length of the object that has the charge, times lambda, which we know is Q1 over L. That's a constant value that we can bring out, times 1 over R squared, which is going to just be L minus X squared plus H squared. But as we know from the last question, we can just go ahead and multiply this denominator of R hat into it and set it equal to 3 halves, or raise it to 3 halves power. Because when you do, like, when you square a square root function and then multiply it by R to the 1/2, or by another square root, you get R times the square root of R, which is R times R to the 1/2, which is R to the 3 halves. Okay, cool. So we'll have L minus X down here plus H squared to the 3 halves power. Oh, the iPad's tweaking. It's crashing out. Times negative L minus X, which I'm just going to go ahead and evaluate to negative LX. I mean, sorry, go ahead and evaluate to X plus L, or X minus L. I mean, let me go ahead and slap this up here, X minus L. Um, yes, that is right. That is true. Okay. And then we have dx. Remember, this is in the Ix direction, so I'll write that as well. So there we go. So we're going to integrate this. This can be written as k q1 over L, 0 to L. Sorry for the handwriting today, guys. I haven't written on an iPad in a while, but okay. So then we have x minus L over L minus X squared plus H squared to 3 power dx. Okay, so this is the point where we're gonna use the formula sheet to help us with this. Okay, so I'm gonna copy this. Cool. This is weird. I don't know when this happened. Oh, oh, it's gone. Okay, that was weird. Okay, so hopefully you have good memory or you're writing this down in your own paper. But um, what we just wrote down for the x component, it looks a lot like this integral here. So, and if it helps, it's better to imagine this as a function of x that we're doing here, f of x squared, for example. And then c would be our h squared, if you're following along at home. And so we're going to use this evaluation to solve the problem instead of actually having to do the u sub and the integration by parts ourselves. So that's what we're going to do. So this is going to come out to be KQ1 over L. Put this bracket here. And we've got -1 up top. L minus x squared plus h squared to the 1/2 power. And that is going to be evaluated from 0 to L. So if we go ahead and do that, we have KQ1 over L, -1. We go ahead and plug in L for x, so that would be 0. So we just have h in the denominator there. And there's one step that I'm forgetting, but I think it would make more sense to add at the end. Maybe. Maybe not. But so that would be what that would be at L. And then we subtract, but add, really, 1 over L minus 0, which would just be L squared plus h squared to the 1/2 power. But I'm just going to write that as a square root. So L squared plus h squared. Cool. All right, so there we go. We got the x component of the field. And I didn't need to add that. Pardon, I was talking about, but okay, so just, really simple problem. Honestly, it took me a while to get these, but I mean, you just gotta, identify what lambda r and r hat are, and then um, put it into an integral and use the formula sheet. In some cases, you might actually have to do a u substitution, but hopefully not. Okay, I'm gonna skip the EY component for now. I'm sorry. If it wasn't 2 a.m., I would totally do it, but um, I'm tired and I have class tomorrow, so we're gonna do that. But we'll move on. So we've got a flux question here. And also the last question is actually pretty good to go through. So a surface which has the shape of a block is located with one corner at the origin. The dimension of the surface area shown below, the surface are shown below. Find the flux of E through the three sides of the surface, labeled 1, 2, and 3, if the electric field is given by that. Okay, so this isn't too bad. Flux is given by the surface area of the electric field through a point over a surface. So that's the law we're using here. So I'm going to do the shaded side first, and that is made up of. So one thing we can do here is, like, if we were to take a chunk out of this front side, we can see that it's made up of dy and dz, right? And so what we're going to do is take the double integral of that side. So side 1, which is the shaded front side that we're looking at, that's facing us. That's going to be the double integral, and we're going to put dy dz in there. Crap. Okay, dy dz. Dy has the limits of immigration 0 to L, sorry, limits of integration. And then dz is 0 to h. Okay. Now, another thing to remember with these questions is the perpendicular. Like if you were to draw an arrow coming straight out of this side of the box, it would be going in the same direction as x. So what we want to integrate is the only vector or the only component that of the field that has ix, because that's the only part that interacts with this side anyway. So we put alpha x squared here. And then one last thing we need to do is evaluate this when x equals w, because this side of the cube or this side of the rectangular prism, whatever, is a distance w away from, well, it's at x equals w. Okay, so that's why we're doing that. But then what we do is we integrate now. Now remember, we can treat alpha x squared as a constant and just bring those outside the front. I mean, honestly, the flux questions are the easiest ones to do for this. But then we would have dy dz. Remember, this is in the ix direction, so it's in the positive ix direction. So we don't really have to worry about the sign. But then we would have basically just, remember, all this is at x equals w. So we would end up just having alpha w squared times L times H. I know that was fast, but that is just because we are integrating one, basically, um, with respect to dy and dz, 0 to L and 0 to H. And so you can just, plop a y in there and then plop a z in there, and then you do L, then you do z, y equals L minus y equals 0. And then so you just have L times H. There you go. Cool. So that's the top, or that's the front side. I'm gonna do the second side and then move on because it is very late. Last time I stayed up this late, I missed my class, so I want to do that. But pretty much the same process for all three sides. But all right, so side two is made up of dx dz, and its arrow is going in the same direction as the y-axis, and so we want to use the iy component now, and so that's going to be from. So we'll do dx dz. X is evaluated from 0 to w, and dz is 0 to h of beta. And again, beta, and then we're going to be integrating this, or actually, we don't need to evaluate this because there is no variable that we need to, specify like we had to with the top or the front side. And so now we have beta. And again, the same thing with this, we could take out alpha x squared because that was a constant. We could take out beta the same way, and then we're integrating it just like we did with these. And so it's just going to end up being beta w h. Yeah, maybe beta w h for the side two. All right, so cool. Side three is really the same thing. You just, it's going in the z direction, and it's made up of dy dx, and so set up the integral the same way, and then just integrate it the same way you would. For this one, you would have to set um, x equal to h, or x equal to w, I mean, again, for the top side. So that's not bad. Okay, last question. And this one was weird, and this one gave us a little bit of trouble when we were working on it today, but it's really an easy question. So what we're going to do here is we've got a force exerted on a test charge by Q naught by charge Q is given by this formula. Okay, so we want to find the electric potential function corresponding to this force if the charge Q were located at the origin And then we also want to find it if it was located at some arbitrary point A, B. So what we want to use here is the equation of, so a couple of concepts we have. We have F equals Q naught E, and then we're also doing V equals the negative integral of the electric field. Okay. And then of course the inverse of that is E equals the gradient of V, the negative gradient of V. So you take negative partial derivatives. That's not necessarily important for this question, but it is just kind of a concept this is synonymous with this. Um, so part A is like we want to find the electric potential at 0, 0 if that charge is at 0, 0. So the electric field in this particular instance, as we know from this formula, is just going to be force divided by Q naught. So the electric field is going to be C times Q over R to the sixth power, R hat. Okay, there we go. So what we then want to do is use this formula for V to solve for the electric potential at 0, 0. And at 0, 0, it's not going to have a radius. Well, I mean, it will, but it's not defined by anything. But there's a difference there, and we'll see that in part B. But so we're going to take the negative integral of CQ over R to the sixth power dr with respect to R. Okay, so we can take out negative CQ, or we can take out CQ, and then just take the integral of R to the negative fifth power. Okay, and that's going to go ahead and be, we're going to add 1. Oh, sorry, this would be to the sixth power. Sorry. We add 1 and divide by the new number, so we have negative CQ, open bracket, 1 over negative 5 times R to the negative fifth power. Okay, and so that's going to end up being CQ over 5R to the fifth for that point. Okay, and that also, don't forget your constant of integration as well. Okay, cool. And then we want part B, where we have this at AB, some point AB. Now, my TA, shout out to the TA. I was talking to him today, and he was like, one thing you could do for this question, especially at point AB, is just kind of draw like a random vector away from it, or just like literally in any direction. And that can kind of help you quantify what's going on. So I'm going to draw a vector just out here arbitrarily, okay? And we're going to draw the components of it as well. So the way this works, right, is because the fact that it's not at the origin anymore, so we have values for r, for the radius. So r for us in this case is going to be x minus a squared plus y minus b squared. And the reason that is because if you think about it, we have this x component of the vector pointing away from the point charge when it's at this point Q, or when it's at AB. And we're going to assume that it's positive, like I said in the first question. So like with the question, you just assume, or the second question with the line charge, we're just going to assume that's positive. So it's pointing away from this point AB in some direction, right? And it could be any direction because point charges give off an electric field in every direction, right? So it doesn't matter. But we're going to use this random direction here. So this is R, and let's say, that's it. And so we're at some value of x and some value of y, right? So here's the value of y, and here's the value of x for these. Oh, that wasn't good. There we go. And so, there we go. So to find the length of this component here, we would just subtract a, because this is a, right? And this is x. So to get this distance here, we just want to subtract a from x. Same thing for y. Okay, so that's where the components are coming from. And then you use the distance formula to find the magnitude of r, or the length of r. Okay. Uh, then what we want to do is throw that into the equation for v. This is v equal to the negative integral of, again, CQ. Um, and really, I mean, like, we don't even have to integrate this again because we really already did it once. And so what we can do is just use this equation here and plug in the value for r that we found. Okay, that's what we're going to do. So we've got v equals CQ over 5 times the square root x minus a squared plus y minus b squared. Y minus b quantity squared, I should say. Dare I say. To the 5th power. And so that would end up just being CQ over 5 times x minus a quantity squared plus y minus b quantity squared to the 5/2 power. And so you could integrate it again, but it's not necessary since we already found the electric potential function given a radius r. We just plugged in a value for the radius this time for part B. Okay, guys, so that is the answer to this last question. I write it all the way down. And then again, of course, don't forget the constant integration. So for part A, we have that over 5r to the 5th plus the constant. And then for part B, we have CQ over 5 x minus a quantity squared plus y minus b quantity squared to 5/2 power, 5/2 plus constant. Okay, cool. So sorry I made this video so late. I know the exam is literally today, but it's been a rough, well, not really rough. It's just been a busy last couple of days, and I honestly have not studied for this exam um, as much as I should have or as I wanted to, but I did have a lot going on, and I was confident that I could at least learn some of it and make a YouTube channel video and get this going. But um, yeah, so most of the questions that I've seen on these past exams kind of look like this and have a kind of a similar format and run the same way. Um, I've seen some that are a little bit different. Like this question 4 is definitely kind of an odd one. I wasn't expecting to see it, but it is here. Um, but then we also, flux is pretty self-explanatory. I would say question 2 is probably the hardest one to do because you have to use calculus. Well, you kind of have to know how to set up the integral and then again using this, which is ironic because they give you the answer practically, but it's still weird. It was weird for me for sure, but then the superposition question is pretty weird, but most of the time they're going to be asking you, like what charge would Q3 need to be for the force to be 0 or like, something like that. And then, again, you just set up these X and Y components like we did here. It's just nice that these canceled out. And I think in most cases they usually will. But I've also seen some superposition questions or line charge questions where, the point charge or the point is on the same axis as the line charge. And that usually makes things a little bit easier. But yeah, I'm gonna try and make one more exam before the. Or I'm gonna try and do one more exam before the actual exam tomorrow. Um, but if I don't, I'm sorry. I will be better prepared for exam 2. Um, but yeah, so if you like this video, you should subscribe to the YouTube channel. I'm just kidding. But if there's a specific exam you want me to do, just let me know in the comments, and I will do it. Hopefully before the exam tomorrow. But I do have a long day. But I will try. I will try. Um, but yeah, that is my run through of exam 1 from 2017. So good luck tomorrow, guys, if you're taking this exam. I don't know. Or, whenever you're watching this video, whoever it is, good luck on your exam. You're going to do great. Um, I might not do great, but you will. I'm giving you my luck. But okay. Thank you for watching. I'll see you again in the next one. Peace.